Hello and welcome to your first official day of AP review. If you can get out a piece of paper, I figure if you take notes on all of these, they'd be good things to study as you're going up to the AP. I'm going to be doing some topical review, some certain topics that are always on the AP. And after we do a little bit of notes, I'm going to try to each day do maybe one AP free response question since those are so important to the AP. So if you have this worksheet out, it's the 2009 AP question 6. We'll do that after the notes. All right, so here we go. So you can just label this AP review. And the topic we're going over today is limits and continuity. Okay, so with limits, what do I always tell you to do first with a limit? Plug in the value. So always try to plug in value first. That's the first thing. Because if the limit's not indeterminate, that's all you need to do. If the limit is indeterminate, there's some things we can try. If limit is indeterminate, and the most common indeterminate form is what? 0 over 0. But other indeterminate forms are infinity over infinity and infinity times 0. So if one of those comes out, one thing you can do, and probably the first thing you did in pre-calc, was try to factor it. If it's set up that way, you can try to multiply by the conjugate. Those are usually radicals, or sometimes trig equations are like that. You can try the trig limit rules, which we did a lot of early in the year. And what I mean by trig limit rules, that's when we said we know the limit as x goes to 0 of sine of x over x is 1, and the same with the limit as x goes to 0 of tan x over x. So you can use those still, but what we do most often now, and probably the best course of action, is the newest method you've used, which is L'Hopital. So L'Hopital's rule can always help you deal with those indeterminate forms. Now, remember, it's just when you take the derivative of the top over derivative of the bottom. So I just want to do a few different examples. Let's start with one of those trig limit ones. If I said the limit as x goes to 0 of sine 5x divided by 3 tangent of 2x. Now again, the first step is what I said to do up here. Always try to plug in value first. So plug in 0. Sine of 0, you should all know by now, is always 0. And on the bottom, tangent of 0 is also 0. So 3 times 0, you're going to get 0 over 0. So it's indeterminate. So this trig limit rules stuff that we did back early in the year, you would have done something like this. You would have said this is equal to the limit as x goes to 0. Remember to watch your notation. I've been a stickler about that all year because the AP is really harsh and will take off points if you don't write things like that. But when I see this, remember if you've got sine of 5x, you can't really pull out the 5 from inside the sign. So you need that to be over 5x on the bottom. As long as these numbers are 1, 5 over 5 or 7 over 7 or whatever, that whole thing is equal to 1. Similarly, we need tan 2x on the bottom because that was there originally. So what has to be on top? 2x. And then this is where we talked about the leftovers or the garbage. So this 5 in front of the x here isn't actually in the denominator in the original thing. So in my garbage area, I need to put a 5 on top so that that cancels out, so that's not really part of it. Similarly, this 2x isn't really part of this top here. So this 2 shouldn't actually be here. So that needs to be on the bottom. The x I don't need to put over here. Why? Because even though it is extra, we've already got one there that wasn't there, and we've got one there that wasn't there, so they're canceling each other out. And the only thing left is this 3 on the bottom. Okay, so then the way we did this was we said, okay, limit as x goes to 0 of sine 5x over 5x is 1. Limit as x goes to 0 of 2x over tan 2x is 1, because remember, it didn't matter what order those were in. As long as one was on the top and one was on the bottom, it didn't matter if it was flip-flopped. So all I'm left with is 5 over 6 times 1. So this is 1 times 5 over 6. So your answer is 5 over 6. Okay, that was our old way to do it. The new way is, since it's 0 over 0, it's indeterminate, you're allowed to do L'Hopital's rule. So L'Hopital's rule would just say this is equal to the limit as x goes to 0 of the derivative of the top. Derivative of sine of stuff is cosine of stuff times the derivative of stuff, so times 5, all over derivative of the bottom. This 3 is just a constant, so that stays there. Derivative of tangent 2x, what's the derivative of tangent? The derivative of tangent is secant squared. So it'd be secant squared 2x times 2. Okay, so I could write this as the limit as x goes to 0 of 5 cosine of 5x all over 3 times 2 is 6. And secant squared 2x is the same as 1 over cosine squared 2x. Now I could deal with that kind of as a complex fraction if I wanted to, but if I plug in 0 right now, what's cosine of 0? 1. So that's equal to 1, 5 times 1. Cosine squared of 2x is just 1 squared, which is also 1. So you can see I'm going to get the same answer. 5 times 1 is 6. 6 times 1 over 1 is 6. There's 5/6. So neither of these is necessarily easy, but you at least have options now. Okay. The other big thing with limits is limits to infinity. Limits to infinity. We're going to use top heavy, bottom heavy, or equal heavy rules. Hopefully you know what those are. I'll review them quick if you don't. That's if it's plus or minus infinity. And that's what I mean by if the limit goes to plus or minus infinity. Or sometimes along with those rules, you might need to partition it. If read in asymptote. Okay, so limits to infinity. Got a few different examples for you here. Here's the first one. Limit as x goes to infinity of 5x squared plus 2x minus 3 all over x cubed minus 7. Now, if you plug in 0 right now, you get infinity on top and you get infinity on the bottom. Sorry, I shouldn't have plugged in 0. If you plug in infinity, you get infinity on top, infinity on the bottom. So technically, it's one of those indeterminate forms I talked about, infinity over infinity. But when we're going to infinity, you want to think of graphically, this is a rational function. And a rational function, as I approach infinity, is approaching a horizontal asymptote. That's the top heavy, bottom heavy, equal heavy stuff. Is this top heavy, bottom heavy, or equal heavy? It's bottom heavy because of that 0 right there. Oops. Or this cubed. This cubed is bigger than this squared, so the degree of the bottom is bigger than the degree on the top. And if it's bottom heavy, what's your asymptote? Big fat 0. So this is equal to 0, and the reason is bottom heavy. Now remember, for some reason they wanted you to show all your work, which doesn't come up too much. But if it said to show your work, we would divide by the highest power of x. So this would be the limit as x goes to infinity of, you would divide everything by x cubed. So it'd be 5x squared over x cubed plus 2x over x cubed minus 3 over x cubed all over x cubed over x cubed minus 7 over x cubed. And then we could reduce that to limit as x goes to infinity of, this would be 5 over x plus 2 over x squared minus 3 over x cubed over 1 minus 7 over x cubed. As x goes to infinity, a constant number over infinity goes to 0. So that's 0, that's 0, that's 0, and that's 0. So this whole thing ends up equaling 0 over 1, which is why it equals 0. So if for some reason a limit to infinity shows up and it says to show all of your work, it's not a bad idea to do this. And actually, if you're on the AP anyways, if you've got the time and you remember to do it, it's probably safer to do that than to use one of our rules. Okay? Okay, let's do a couple more here. I want to do the limit as x goes to negative infinity of 5x to the 7th minus 2x to the 4th minus 1 all over negative 2x squared plus 5. Top heavy, bottom heavy, or equal heavy? This one's top heavy, and top heavy is the hard one, because top heavy means you have a slant asymptote, which depending on which way the asymptote is slanting, you're going to positive or negative infinity. So I circled this because you need to look at the leading coefficients on the top and bottom. This is going to essentially turn into what happens to 5x to the 7th over negative 2x squared, which is negative 5 halves x to the 5th. And in order to figure out what's happening as x goes to, in this case, negative infinity, so it's important which way I'm going, I got to think of what the tails would look like of negative 5 halves x to the 5th. So it's a negative odd. So odd polynomials are the snaky graphs. If it's negative, it starts up and goes down. So if I go to negative infinity, as x goes to negative infinity, my y's are going to positive infinity. So the answer to this is positive infinity. Okay, 2 more limits, and then we'll talk a little bit about continuity. How about the limit as x goes to 3 of 5 over x squared minus 9? First off, what do you get if you plug in 0, or plug in 3? You get 5 over 0. So that's not indeterminate. That's not 0 over 0. It's not infinity over infinity or infinity times 0. So not indeterminate. It's also not bottom heavy. Don't say it's 0. Why can't you say it's bottom heavy? Because it's not a limit to infinity. That's important to note. Not to plus or minus infinity. Don't use bottom heavy. Bottom heavy is only talking about asymptotes, and asymptotes are only about what happens as you go to positive or negative infinity. So this is what I meant by or partition it if we're at an asymptote, because that's what is happening here. X equals 3 is a vertical asymptote. So what does that mean? Well, 3 is the area we're worried about. So 3 is a vertical asymptote, technically. If I go left of 3, if I use 0, I have 5 over negative 9, so that'd be negative over here. And if I go greater than 3, like 4, 5 over something positive is positive. So since this is an asymptote, it's going to look something like this. So the limit as x goes to 3 goes to negative infinity from the left, positive infinity from the right. So what does that mean about the limit at 3? It does not exist. So when it's over 0 like this, you might get does not exist. If for some reason these were both positive, the answer would have been infinity. Or if they were both negative, the answer would have been negative infinity. So that's why you have to partition. All right, last one like this. Actually, it's a little bit different, but this shows up in review a lot, and the AP loves it. Limit as h goes to 0 of ln of e plus h minus 1 all over h. What would I tell you to do first? Plug it in. I plug in 0. What's ln of e? It cancels, but it cancels to 1. So 1 minus 1 is 0 over 0. So what could I do? Right, I could do L'Hopital. If I do L'Hopital, derivative of the top, ln of stuff's derivative is 1 over stuff. Technically times the derivative of stuff. What's the derivative of e plus h? E is a constant, so that goes away. H is the variable, so the derivative is just 1. Minus 1, what happens to that? Constant goes away, all over 1. And remember, this isn't okay. You either need to write limit as h goes to 0, or you need to write evaluated at h equals 0. If I plug in 0, I'm going to end up with 1 over e. Probably the easiest way to approach that. The tricky way that you have seen before is when you see this something plus h, that's really the difference quotient in disguise. And remember, difference quotient is limit as h goes to 0 of f of x plus h minus f of x all over h. And what's that definition of? The derivative. That's f prime of x. So when I see e plus h, that's kind of like x plus h. So that means what would f of x have been? Just ln of x. Because f of x plus h would be ln of x plus h. Now the other thing is there's an e in here. So that means x is really e. So instead of looking for f prime of x, we're basically looking for f prime of e. So if I realize my function's ln of x, then f prime of x is 1 over x, and f prime of e is 1 over e. But you can see I can get that from L'Hopital also. But just recognize that trick. If you see something plus h, could be just difference quotient, x plus h. The 1 is minus f of e, because ln of e is 1. Okay, so there's some limit review. I'm going to flip the page and talk a little bit about continuity. Continuity, another early topic we did. A function is continuous at x equals a if the limit as x approaches a of f of x exists. The function at a, f of a, exists. Anyone remember the third qualification? those two things have to be equal. The limit as x goes to a of f of x has to be f of a. Now, you'll see in a second, in order to check if the limit exists, just know that you may need to check if the limit as x goes to a from the left of f of x equals the limit as x goes to a from the right of f of x. Especially if it's a piecewise function and you're at one of those breaks, in order for the limit to exist, the left-hand limit has to equal the right-hand limit. Okay. Two notes with continuity, and I'll give you an example. Continuity does not imply differentiable. We've seen that a couple times this year. Just because a function is continuous does not mean it's differentiable. What's the easiest counterexample to that? Right, the absolute value function. If I have any sort of absolute value, it's def continuous, but what's the problem? Those corners. This is not differentiable here. You can't take the derivative at a corner. Just because it's continuous does not mean it's differentiable. And think of the absolute value function if you're questioning that ever. The other way is true, though. If it is differentiable, differentiable does imply that it's got to be continuous. If you're able to take the derivative, the function's definitely continuous. Okay, I just got one example of continuity for you, and it's from the Barron's review. I'm not sure if it's a question you had to do or if it's one like it, but just FYI, this is Barron's review, page 105, number 27. And basically it says let f of x equal the piecewise function x squared plus x over x if x isn't 0, and it's 1 if x is 0. And the question is it continuous at x equals 0? Okay, well, in order to do this, I'm going to check those three conditions. So first thing I'd want to check, does the limit as x goes to 0 of f of x exist? Well, 0 is the issue. So the limit as x goes to 0 of f of x is equal to, which would I use here? I'd use this top equation because the limit is always what happens to a function as it gets really close to, but not including 0. So since this is the same function on the left and the right, I don't have to check left-hand limit and right-hand limit in this case. I can just say this is equal to the limit as x goes to 0 of x squared plus x over x, which is 0 over 0. So I could either factor or we can use L'Hopital. So if I use L'Hopital, top would become 2x plus 1 over 1. Derivative of the top, derivative of the bottom. Plug in 0, you get 1. So the derivative, or sorry, the limit exists. Second step, does the function exist? Does f of 0 exist? And the answer is yes. F of 0, if x is 0, it's equal to 1. So yup, that exists. And then the third thing and the final thing is the limit as x goes to 0 of f of x equal to the function evaluated at f of 0. And since both 1 and 2 were 1, those are equal. So therefore, f of x is continuous at x equals 0. So if either of these turned out to be does not exist, it'd be discontinuous. If these were two different numbers, that would also be discontinuous. but that's how you check for continuity. Okay, so that's the notes that I want to do. And every day I do notes, I would also like to do a certain AP review question. Now, these free response questions are obviously hugely important this year. And I want to do some frequently used types of these free response questions that you'll start seeing more and more of. And I want to go through the strategies of how to recognize them and know what to do. So if you're able to, if you have this in front of you, great. If you're able to print it out, that's probably preferable. If not, definitely write down this on a separate sheet of paper. You can even write down which question it was. You can go back and look at it later. But this is from 2009, and it's question 6. So this would have been a no calculator question. The velocity of a particle moving along the x-axis is modeled by a differentiable function v, where the position x is measured in meters and time t is measured in seconds. Selected values of v of t are given in the table above. The particle is at position 7 meters when t equals 0. Okay. They're giving you information about the position, and they're giving you the table of velocity. Part A, estimate the acceleration of the particle at t equals 36 seconds. Show the computations that lead to your answer. Indicate units of measure. Okay, I'm going to come down here. All right, so I want acceleration. All I have is a table with velocity. How do I get acceleration from velocity? It's the derivative, right? Oops. So acceleration is equal to v prime. Now I've said all year, when you hear derivative in calculus, what should you immediately think of? Slope. Okay. Now, I want to get the slope off of a table. And all I can do is, it says estimate it, so all I can do is get the best estimate. So the idea when it's asking for the slope or the derivative of a table, best estimate of the slope you can get from a table is using change in y over change in x of points that are nearby. And that's something that does come up quite a bit on these free response questions. So usually you're used to just taking the derivative because you have an equation. But if I don't have an equation and I only have certain points on a table, if I want specifically, in this case, t equals 36, 36 is between 32 and 40. So the best I can do, I know at 32 I'm at -4, at 40 I'm at 7. If I get a slope between that, that slope should be about what the acceleration would be. So v prime of 36 is going to equal change in y, which is 7 minus -4 over change in x, which is 40 minus 32, which is going to be 11 over 8. And it says to use units, indicate units of measure. So change in y was meters per second divided by seconds. So it's going to be, like any velocity would be, meters per second squared. Okay, that's part A. Not hard to do, but maybe confusing to know what to do. That's why I'm going over these. Okay, part B, using correct units, explain the meaning of the integral from 20 to 40 of v of t dt in the context of this problem. Use a trapezoidal sum with 3 subintervals indicated by the data in the table to approximate this. Okay, integral of velocity. So the integral from 20 to 40 of v of t dt. If you take the integral of velocity, what do you get? You get position. So using fundamental theorem, the antiderivative of velocity is position. So this would be the position at 40 minus the position at 20. When you think about it like that, it might make it a little bit more obvious what it means. It's some particle moving. Here's where it was at time 40. Here's where it was at time 20. So if I subtract those, we get, careful in saying distance traveled, it's the displacement, where it's ended minus where it started. So in the context of this problem, this would be the displacement or change in position. Don't say distance unless it was absolute value. Between t equals 20 and t equals 40. So explain always means in words. And then the second part, again, is something that does come up a lot. We want to estimate this integral, and we can do that with a Riemann sum. In this case, they want us to use a trapezoidal sum with 3 subintervals indicated by the data in the table. Okay, so this is why using that calculator program isn't always all that helpful. Because the calculator program, if you remember using the trapezoidal sums or Riemann sum program, you needed an equation. Well, I don't have an equation. I have a table, and this is what the AP usually does. So I'm specifically looking between 20 and 40, and it says 3 subintervals. Well, here's subinterval 1, here's 2, here's 3. I like to draw that out to show you. I mean, maybe I have some sort of crazy graph. I'm not sure exactly what it looks like, but here's the trapezoids I'm trying to evaluate. Okay, so I have 3 trapezoids. So if I wanted to estimate the integral from 20 to 40 of v of t dt using a trapezoidal sum, we need to know the area of a trapezoid. What is that? Yeah, not so easy to remember sometimes. It's 1/2 times the height times base 1 plus base 2. Remember how we did that with the Riemann sums. The height, you kind of want to think of it as the side. So this is the height of my trapezoid. That's h. This is base 1. This is base 2. Now the other thing you might notice about these tables is the intervals aren't all equal. Here the height's 5, but here it's 7, and here it's 8. So you really just have to take 3 areas and add them together. Okay, so I can pull the 1/2 out front, but let's just do 3 areas. The first one's going to be 1/2 times 5 times the first height is -10, and the second one's -8. So 1/2 times 5 times -10 plus -8 plus 1/2 times the second trapezoid height is 7 times the height of -8 plus -4. So 7, -8 plus -4. And the last one is 1/2 times the height of 8 times -4 plus 7. Okay, that's going to equal, this is -18 divided by 2 is -9 times 5, that's -45, plus, this is -12, half of that would be -6, times 7 is -43, plus, this would be, well, 1/2 of 8 is 4, and 4 times 3 is 12, so I have -45 plus -43 plus 12. -45 plus -43 plus 12 is -76. Just say indicate units of measure. Nope, but it would be meters. And of course, you should have all been screaming at me because negative 12, negative 6 times 7 is negative 42. So this is actually negative 75 meters. Sorry about that. Don't complain. Okay, so those are very common questions. Let's go to C. Between 0 and 40, must the particle change direction in any of the subintervals indicated by the data in the table? If so, identify the subintervals and explain your reasoning. If not, explain why not. Okay, you got to break it down. If the particle changes direction, what's true about the velocity? There's a sign change. So change direction implies velocity changes signs. Now, the other important thing to notice about this is that up here it says it's modeled by a differentiable function. If it's differentiable, what does that imply? Differentiable does imply continuous. We just talked about that. So that means that if it's positive 5 here and negative 10 here, it's got to cross over the x-axis. It's got to hit 0 between that, which means it's going to change direction. So it's going to change direction here, and where else? Here. Anytime we change from positive to negative or negative to positive, we're changing directions. So for part C, the answer would be yes. Changes direction. Between t is 8 and 20. So between 8 is less than t is less than 20. And this other spot, 32 to 40. 32 is less than t is less than 40. And it says explain your reasoning. It's just because velocity changes signs there. Okay, so again, part C, not that tricky, but you have to break it down to know what it's asking. Changes direction means velocity changes sign. Okay, last part. Suppose that the acceleration of the particle is positive between 0 and 8. Explain why the position of the particle at t equals 8 seconds must be greater than 30 meters. This one's kind of tricky. Again, break it down. What does it mean? Why would they tell you this first part? Acceleration is positive between 0 and 8. So maybe just think about what that means. So acceleration positive between 0 is less than t is less than 8. Acceleration is the slope of velocity. Okay, so if the slope of velocity is positive, that means velocity is increasing. Okay, so I know that velocity at 0 is 3, velocity at 8 is 5. Okay, but at this point, if I want to know information about the position at time 8, how would I get position from velocity? I would take the integral. And if I take the integral from 0 to 8 of the velocity, that's equal to the position at 8 minus the position at 0. I know I used s up here. S or x is usually position. Okay, I'm looking for this. I'm trying to prove that this has to be greater than 30. So that's why I used 8. Why did I use 0? Well, because I know at x equals 7 meters, we're at 0 seconds. So I know that this piece is equal to 7. I'm looking for information about x of 8. Okay, so now finally I have to figure out how do I evaluate this. Well, we could kind of do a Riemann sum, maybe, but all I really have is one block here. But look at what that means. So I know from 0 to 8, what's the velocity equation look like? Well, I know at 0 I'm at 3, because it tells me. And I know that velocity is increasing because the acceleration is positive. So even though I know that by the time I get to 8, it ends at 5, I don't know how it gets there, but I know that the velocity is increasing. It's increasing somehow. It's never decreasing. It's always increasing because the acceleration is always positive. So what I can say for sure is I know it was at 3. If I use kind of like a left Riemann sum here, what's the area of that square or rectangle I just drew? 3 times 8 is 24. So even if I just use a left Riemann sum, I know that the actual velocity is going to be bigger than that. So I know that the area, or the integral of velocity between 0 and 8, has to be greater than 24. 24 is the minimum it can be, because that's the lowest the velocity is on that interval, because it's always increasing. So that means if I add this 7 over, x of 8 has to be greater than 31, and I've just proved what I wanted to show. I wanted to show it has to be greater than 30 meters. Well, I proved that it has to be greater than 31 meters. It says explain, so we should kind of put some words involved here. So everything I just showed you proves it, but in words, we could say since v of t is increasing, the minimum value would be 3. Therefore, the integral from 0 to 8 of v of t dt is going to be greater than 24 when x is 0, or when t is 0, the position is 7. When that is added, we get that x of 8 has to be greater than 31, but what we're just trying to prove is greater than 30. So when it says explain, talk about your work, talk about what you're doing. That's all I did. You don't need to be a math teacher to write this. Since it's increasing, the minimum value would be 3, which is what I talked about here. Therefore, the integral is bigger than 24. And when you add that position at 0, it's got to be bigger than 30. Okay. So again, I don't expect this to seem easy, but this is a typical free response question. So when you see things like this, if you see a table, if you want the slope, the derivative, you're going to take the slope. If you want the antiderivative, you're going to do some sort of Riemann sum. That's the big things to remember. All right, so try tonight's review assignment. Stay up to date with those. It's super important. Let me know if you got any questions. Good luck.